Today we're going to talk about inclined planes. But before we get into that, let's refresh our memories on forces when an object is resting on a flat surface. So when an object is resting on a flat surface, the forces acting in the same direction can conveniently be used in the same equation. Right? So for instance, a rightward force of 302 newtons is applied to a 28.6 kilogram crate to accelerate it across the floor. Coefficient of friction between the crate and the floor is 0.75. Determine the acceleration. So let's make a free body diagram here. I know that force of gravity is directed down. It's sitting on a flat surface, so normal force is directed perpendicular to that. It looks like a rightward force, so I have an applied force here. And it tells me that friction is present. So I know that friction prevents its motion, so it's acting in the opposite direction. Now, if I'm trying to find the acceleration of the crate, right, if it's moving in the horizontal, I'm going to look at the forces acting in the horizontal. Now, applied force and frictional force are, like I said, conveniently acting on the same plane, so we can use them in the same equation, right? We can't, for instance, use applied force and gravity in the same equation because they're not on the same plane. So I'll set net force is equal to MA. Break this up into the force in the direction of motion minus the force opposing motion. I'm trying to find, let's see, what am I trying to find? The acceleration. So the applied force was 302 newtons. Gives me a coefficient, not a frictional force. So I know that friction is equal to mu Fn. Because it's resting on a flat surface, normal force is equal to the force of gravity. And force of gravity is equal to mass times gravity. So I can replace this with mu times mass times gravity. Let's say this for now. Is equal to MA. Now let's plug in numbers. So 302 newtons of force, coefficient is 0.75, mass is 28.6, gravity is 9.8, mass is 28.6 again, times A. So I get an acceleration of 3.2 meters per second squared. So if any forces acting on the system exist at an angle, that force needs to be broken down into its x and y components, kind of like when we talked about equilibrium. So what would the acceleration be if you pushed the 10 kilogram box with a 50 Newton force down at an angle 30 degrees below the horizontal? So now that applied force is going to be at 30 degrees below the horizontal, at 50 Newton force. If the force of friction between the box and the floor is measured to be 19.6 newtons. So I can't just use this force and this force in the same equation because they're not on the same plane, right? But what I can use is the x component of that force, right? So I'm going to say the x component of that push force is in the direction of motion, friction is opposing motion, is equal to ma. So that would be force of the push times cosine of the angle minus ff is equal to ma. Now we can plug in numbers because I know that the push force is 50 newtons times the cosine of 30 degrees minus the 19.6 newtons of frictional force is equal to 10 times acceleration. So I get an acceleration of 2.4 meters per second squared. All right, so Now let's look at an object resting on an actual incline. When an object rests on an incline, it will only accelerate along the surface. Luckily, forces like friction and the normal force already exist on the proper planes, right? Because friction is always parallel to the surface it's resting on, and normal force is always perpendicular to the object it's resting on, right? But unfortunately, gravity is always directed straight down. So that force is always going to exist at an angle. Let's draw a free body diagram for a box on an inclined plane and see what forces are equal and opposite to each other. So here's my example, right? Obviously, like I had drawn on the other picture, normal force is always perpendicular to the surface it's resting on. Force of friction is always parallel to the surface, but opposite motion. And then force of gravity is always directed straight down. These vectors are not to scale. Okay, so I need to figure out what is equal and opposite to that normal force. So to do that, I'm going to draw a triangle. Okay, so I'm going to make this a triangle. This angle, the angle of the incline, is equal to that angle. Now this component of the force of gravity, I'm going to refer to that as FGX because it is parallel to the x-axis. And I'm going to refer to this as FGY because it is on the same plane as our new y-axis. So, which set of forces could be used in the same equation? Well, I know that, let's look at the vertical first, right? The normal force could be used in the same equation as the y component of the force of gravity. The force of friction and x component of the force of gravity, those are also on the same plane. So force of friction and FGX could be used. Now FGY, let's come up with an equation for that, right? So that is the adjacent vector to the force of gravity angle. So because of that, I'm going to say that FGY is equal to force of gravity times the cosine of the angle. The x component is opposite to that angle. So I'm going to say that FGX is equal to FG times the sine of the angle. Okay. So let's do some practice problems with that. A box is sliding down a ramp at a constant velocity. Derive an equation for the frictional force acting against the block. Well, I know that if it's moving at a constant velocity, the frictional force opposing its motion is equal to the x component of the force of gravity. Oops. I also know then that this would be equal to FG sine of the angle, and I can break this down into mass times gravity times sine of the angle. So if an object is sliding down at a constant velocity, force of friction would be equal to that. All right. A Land Rover ads used to claim that their vehicles could climb a 45-degree slope. What is the minimum coefficient of static friction that allows this to be possible? Well, I know that the force of friction would be equal to the force of gravity in the x direction if it was at rest, and we know it's at rest because we're talking about static friction. And I know that force of friction is equal to mu Fn. And I know force of gravity is equal to Fg sine theta. Now, this is where it's a little different because in our last couple problems, we said that object resting on a flat surface, the normal was equal to the force of gravity. But normal doesn't equal force of gravity anymore, right? Normal force is now equal to the y component of the force of gravity, right? So we can't just replace normal force with mg. We have to replace it with something a little more specific, and that would be the force of gravity times the cosine of that angle, right? Or mg cosine angle, right? So let's replace it. So I have the coefficient times mg cosine theta is equal to mg sine theta. So if I'm trying to find the coefficient of friction, let's divide both sides by this. MG's will cancel, so I just have sine over cosine, which give me a coefficient of 1. So the friction between the tires and the road would have to be 1 in order for that claim to be true. And lastly, a 4,000 kilogram car is parked on a 7-degree slope. How big is the frictional force acting on the car? Well, I know that frictional force, if it's parked, that means frictional force is equal to the x component of the force of gravity. I know that Fgx is equal to mg sine theta. So if I take 4,000 kilograms times 9.8 times the sine of that 7-degree slope, I get a frictional force of 477 newtons. So that's it for the basics. Be prepared to work through a couple more examples when we get to class next time. See you then.